In this video, we are going to study indeterminate forms. Suppose fx and gx are two real-valued functions, and let limit fx as x tends to a is 0 and limit gx as x tends to a is also 0. Then limit fx upon gx as x tends to a will be 0 upon 0, which is an indeterminate quantity. And suppose this first limit is infinity and the second limit is also infinity, then limit fx upon gx as x tends to a will be infinity upon infinity, and limit fx as x tends to a multiplied by limit gx as x tends to a will be 0 into infinity, and limit fx as x tends to a minus limit gx as x tends to a will be infinity minus infinity. So the limits of the type 0 upon 0, infinity upon infinity, 0 into infinity, infinity minus infinity are indeterminate in nature. That means they cannot be evaluated as they are. So we have to devise a method to evaluate these indeterminate forms. The indeterminate forms are of the type 0 into infinity, 0 upon 0, infinity upon infinity, infinity minus infinity, 1 raised to infinity, 0 raised to 0, and infinity raised to 0. We are going to see how these indeterminate forms can be evaluated. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. There is a rule to evaluate these indeterminate forms known as L'Hopital's rule, which says limit fx upon gx as x tends to a is limit f dash x upon g dash x as x tends to a, provided this second limit exists. As per Taylor series, we can expand fx and gx as power series of x minus a in the neighborhood of a. For example, we can expand fx as fx equals fa plus x minus a f dash a plus x minus a whole square upon 2 factorial f double dash a plus x minus a whole cube upon 3 factorial f triple dash a plus so on and so forth up to infinity. So expanding fx and gx by Taylor series will help us to understand this L'Hopital's rule. L'Hopital's rule states that if fx and gx, which can be expanded by Taylor series in the neighborhood of x minus a, and if fa equals ga equals 0, then we have limit fx upon gx as x tends to a is limit f dash x upon g dash x as x tends to a, provided this limit exists. So by Taylor series, we can write this fx upon gx as fa plus x minus a f dash a plus x minus a whole square upon 2 factorial f double dash a plus so on and so forth upon ga plus x minus a g dash a plus x minus a whole square upon 2 factorial g double dash a plus so on and so forth. Now since fa equals ga each equals 0, dividing this numerator by x minus a and denominator by x minus a gives us fa is 0, x minus a upon x minus a is 1. So it will be f dash a plus x minus a whole square upon x minus a will be x minus a upon 2 f double dash a plus so on and so forth upon, since GA is 0, it will be 0. X minus a upon x minus a will be 1. So it will be just G dash a plus x minus a whole square upon x minus a will be x minus a upon 2 factorial G double dash a plus so on and so forth. Now taking limits on both sides, as x tends to a, this will be limit fx upon gx as x tends to a equals limit f dash a plus x minus a upon 2 factorial f double dash a plus so on and so forth upon g dash a plus x minus a upon 2 factorial g double dash a plus so on and so forth as x tends to a. This will be f dash a upon g dash a, because as x tends to a, all these terms will become 0. But f dash a upon g dash a is limit f dash x upon g dash x as x tends to a. Thus we get L'Hopital's rule, limit fx upon gx as x tends to a equals limit f dash x upon g dash x as x tends to a. First, we will discuss indeterminate form 0 upon 0. We know that limit sin x upon x as x tends to 0 is 1. This we have evaluated by using a theorem known as sandwich theorem. But if we try to solve it by direct substitution, this will become equals sin 0 upon 0, 0 upon 0. So this limit is indeterminate form of the type 0 upon 0. We can easily evaluate this indeterminate form by using L'Hopital's rule and write limit sin x upon x as x tends to 0 equals limit d by dx of sin x upon d by dx of x as x tends to 0. This will be limit cos x upon 1 as x tends to 0. So this limit will be cos 0, 1, same as this one. So we can see without using sandwich theorem how easily we can evaluate this limit sin x upon x as x tends to 0 equals 1 by using L'Hopital's rule. We know that limit a raised to x minus 1 upon x as x tends to 0 is log a. This limit will be a raised to 0 minus 1 upon 0, 1 minus 1 0 upon 0. So this limit is of the type indeterminate form 0 upon 0. Now we will apply L'Hopital's rule to evaluate this limit. So according to L'Hopital's rule, this limit will be limit d by dx of a raised to x minus 1 upon d by dx of x as x tends to 0. This will be limit a raised to x log a minus 0 upon 1 as x tends to 0. This limit will be a raised to 0 log a, same as this log a. So we can see by using L'Hopital's rule how easily we can evaluate indeterminate form 0 upon 0. How to evaluate limit x minus sin x upon x cube as x tends to 0. If we substitute 0 in place of this x and this x, it will be of 0 upon 0 indeterminate form. So we have to apply L'Hopital's rule. This will become limit d by dx of x minus sin x upon d minus dx of x cube as x tends to 0. This will be limit 1 minus cos x upon 3x square as x tends to 0. This again is 0 upon 0 indeterminate form. So we have to apply L'Hopital's rule again. This will be limit derivative of 1 minus x will be 0 minus sin x upon derivative of 3x square 6x as x tends to 0. This again is 0 upon 0 indeterminate form. We have to apply L'Hopital's rule again. So this limit will become derivative of sin x cos x upon derivative of 6x. 6 as x tends to 0. This will be 1 upon 6 cos 0, 1 upon 6. How to evaluate limit x raised to x minus x upon x minus 1 minus log x as x tends to 1. If we substitute 1 in place of x here, this will be 0 upon 0 indeterminate form because log 1 is 0. So we have to apply L'Hopital's rule. But before that, we have to find derivative of x raised to x. So let y equals x raised to x. We have to take logs on both sides. So this will be log y equals log x raised to x, which according to laws of logarithm x log x. Now we will differentiate this with respect to x. So derivative of log y is 1 upon y dy by dx equals derivative of x log x by product rule. First function x into derivative of log x 1 upon x plus second function log x into derivative of first, that is derivative of x, which is 1. Cancelling x, we get 1 plus log x. So dy by dx will be y into 1 plus log x, but y is x raised to x. So dy by dx will be x raised to x into 1 plus log x. Now we will apply L'Hopital's rule and write this limit d by dx of x raised to x minus x upon d by dx of x minus 1 minus log x as x tends to 1. This will be limit derivative of x raised to x is x raised to x into 1 plus log x minus derivative of x is 1 upon derivative of x 1 minus derivative of 1 0 minus derivative of log x 1 upon x as x tends to 1. If we substitute x equals 1, this again will become 0 upon 0 indeterminate form. So we have to apply L'Hopital's rule once again. So this will be limit d by dx of x raised to x into 1 plus log x minus 1 upon d by dx of 1 minus 1 upon x as x tends to 1. This will be limit. We will apply product rule for these two functions. So first function x raised to x into derivative of second, derivative of 1 plus log x is 1 upon x plus second function 1 plus log x into derivative of first, that is derivative of x raised to x, which is this x raised to x into 1 plus log x. So 1 plus log x into 1 plus log x will be 1 plus log x whole square into x raised to x upon derivative of 1 minus 1 upon x will be minus of derivative of 1 upon x is minus 1 upon x square as x tends to 1. So we can substitute x equals 1 here. So that will be 1 raised to 1, 1, 1 upon x, 1. Then log 1 is 0. So this will be 1 square, which is 1. And 1 raised to 1, again 1. So this will be 1 plus 1, 2 upon 1 square, that is 1. So the value of limit is 2. We are given that limit sin 2x plus a sin x upon x cube as x tends to 0 to be finite. We have to find value of a and hence the limit. Now the given limit is 0 upon 0 indeterminate form. We can apply L'Hopital's rule and write derivative of sin 2x 2 cos 2x plus derivative of a sin x a cos x upon derivative of x cube 3x square. Numerator will be 2 cos 0, which is 1, plus a cos 0, which is a, equals 0. So the limit becomes limit 2 cos 2x minus 2 cos x upon 3x square as x tends to 0. This again is a 0 upon 0 indeterminate form. So we apply L'Hopital's rule and write limit derivative of cos 2x is 2 into minus 2 sin 2x into 2 minus 2, derivative of cos x is minus sin x upon derivative of 3x square 6x as x tends to 0, which is this also is a 0 upon 0 indeterminate form. So we again apply L'Hopital's rule and the limit will be minus 8 cos 2x plus 2 cos x upon 6 as x tends to 0. So the limit will be minus 8 cos 0 is 1 plus 2 cos 0 is 1 upon 6 minus 6 upon 6 minus 1. So this is the value of the limit. If limit x into 1 plus a cos x minus b sin x upon x cube as x tends to 0 is 1, we have to find a and b. Now this given limit is a 0 upon 0 indeterminate form. So we will apply L'Hopital's rule and write limit. Now derivative of x into 1 plus a cos x by product rule will be first function x into derivative of second function 1 plus a cos x, which is minus a sin x, plus second function 1 plus a cos x into derivative of first, that is derivative of x is 1, minus derivative of b sin x is minus b cos x upon derivative of x cube 3x square as x tends to 0. We will name this 1. Now here as x tends to 0, denominator 3x square tends to 0 and the numerator tends to this part to 0, and these two parts together will tend to this 1 plus this a minus b, but this limit is finite and given to be 1. Therefore this numerator 1 plus a minus b will tend to 0. So we will write 1 plus a minus b equals 0. That gives a minus b equals minus 1. We will name this equation 2. Now the limit in equation 1 is indeterminate 0 upon 0 form. So we have to apply L'Hopital's rule that will give limit minus a into derivative of x sin x is x cos x plus sin x plus derivative of 1 plus a cos x will be minus a sin x plus b sin x upon 6x as x tends to 0. The numerator will be minus ax cos x plus this b minus this a and this a 2a sin x upon this 6x. Now this again is 0 upon 0 indeterminate form. So we have to apply L'Hopital's rule. That will be limit derivative of minus ax cos x by product rule minus ax into derivative of cos x minus sin x plus minus a cos x into derivative of x, which is 1, plus this b minus 2a derivative of sin x cos x upon derivative of 6x 6 as x tends to 0. Now as x tends to 0, the limit will be this b minus 2a minus this a, it will be b minus 3a upon 6, which is given to be 1 here. So this will be b minus 3a equals 6, and here we have a minus b equals minus 1. Adding these two equations, b minus b will be 0. So minus 2a will be 5, a will be minus 5 upon 2, and b will be minus 5 upon 2 plus 1 minus 3 upon 2. So a equals minus 5 upon 2 and b equals minus 3 upon 2 are the values of a and b. We are given limit a sin square x plus b log cos x upon x raised to 4 as x tends to 0 to be 1 upon 2, and we have to find values of a and b. As we can see, this limit is of 0 upon 0 indeterminate form. So we have to apply L'Hopital's rule and write limit as x tends to 0 derivative of a sin square x to a sin x cos x plus derivative of b log cos x, which is b upon cos x into minus sin x upon derivative of x raised to 4 4x cube as x tends to 0. This again is a 0 upon 0 indeterminate form. So we have to apply L'Hopital's rule. So limit here 2a sin x cos x will be a sin 2x, because 2 sin x cos x is sin 2x, and this will be minus b tan x. Derivative of a sin 2x will be 2a cos 2x minus derivative of b tan x is b sec square x upon derivative of 4x cube will be 12x square. Now as x tends to 0, denominator 12x square also tends to 0, and the numerator tends to this 2a because cos 0 is 1 minus this b because sec square 0 is also 1 equals 0. We name this equation 1. Applying L'Hopital's rule, once again derivative of 2a cos 2x will be minus 4a sin 2x minus derivative of b sec square x will be 2b sec x into sec x tan x upon derivative of 12x square 24x. This will be minus 2b sec square x tan x. This we further write as minus 2b. In place of sec square x we write 1 plus tan square x into this tan x. So the limit reduces to minus 4a sin 2x minus 2b tan x minus 2b tan cube x upon 24x. This again is a 0 upon 0 indeterminate form. Let us write this 2a minus b equals 0 here. Applying L'Hopital's rule on this limit, it will be limit derivative of minus 4a sin 2x is minus 8a cos 2x minus derivative of 2b tan x is 2b sec square x. Derivative of minus 2b tan cube x is minus 6b tan square x into sec square x upon derivative of 24 as x tends to 0. As x tends to 0, this cos 2x tends to 1, this sec square x tends to 1, and tan square x tends to 0. So the numerator tends to minus 8a minus 2b upon 24, and the value of this limit is given to be 1 upon 2. That will be minus 4a minus b equals 6. We name this 2. Now we will solve equation 1 and equation 2 simultaneously. So writing 2a minus b equals 0 here and subtracting minus b plus b 0. So minus 6a equals 6, a equals minus 1, and minus 2 minus b equals 0. So b equals minus 2. So a equals minus 1 and b equals minus 2 are the values of a and b. Friends, if you like this video, please click the like button. Share this video with your classmates. Don't forget to subscribe this channel. Make constructive comments to help improve my videos. See you in the next video. Until then, keep watching Number Collage. Thank you.